Welcome back. In our previous lecture, we discussed about axial momentum theory, where the velocity is constrained in a particular constraint to a single axis. So what we discussed is, so we talked about axial momentum theory. So where the flow is assumed to be uniform incompressible and inviscid. So is also unidirectional, where the velocity has only one component from left to right, and then we also assume that the thrust generated is uniform or equally distributed throughout the disk, across the disk of area A, right. So because of this, disk induces velocity Vi to the flow, and due to which there is a jump in total pressure and the static pressure. Across the disk. So we unidirectional, and then this thrust is generated by a disk of very thin thickness. So with these assumptions, we witnessed at a location, say at a location 2, where the pressure in the downstream is equals to atmospheric pressure. So we have the cross section area of the stream tube is figured out to be half the cross section area of this disk, half the area of this disk, and then the velocity at this particular location is equals to twice the velocity induced by the disk. So let Vi be the velocity induced by the disk, where PL is a pressure to the left of the disk and PR is a pressure to the right of the disk, and we are talking about static pressure here, and then P infinity be the pressure far ahead of this disk, where V infinity is close to 0 here, right. Okay, and we also figured out that thrust generated can be calculated or can be estimated by means of the pressure generated, right. Pressure difference generated by the disk or imparted by the disk across the cross-section disk of cross-section area A, which is equals to mass flow rate times Ei times V2, right. So from here we related Vi is equals to 1 upon root over 2 rho times root over T by A, where T by A is known as thrust loading. So Vi induced velocity depends upon this thrust loading factor T by A, right. And also we witnessed the power induced is equals to thrust times thrust generated times or thrust imparted on the fluid times the corresponding velocity imparted to the fluid Vi, right. So now let's look at the circular cylinder So it's a side view of the circular cylinder, right? So when you place this circular cylinder in the atmosphere, so what do you think are the forces acting on it? So it is surrounded by the gas, right, atmosphere here, which exerts equal pressure in all directions, isn't it? So the pressure exerted by the atmosphere on this cylinder is equal in all directions, and the corresponding force or the net force due to this will be 0, isn't it? Because pressure acts in all directions and the net force is 0. So if I want to lift this cylinder up, right, the force that I need to overcome is weight of the cylinder mg, isn't it? I need to produce a force which will overcome the weight of this object here, right? So we have surrounding atmosphere, and then it exerts some static pressure on this, but which is equal in all directions. So the total force exerted from the top or from any direction because of this atmospheric pressure is cancelled from the opposite part on the cylinder. So we don't get any useful lift, or I try to constrain myself using the word lift for the time being. So useful force that will lift this body from the atmosphere under static condition, right? So let's look at what happens when we place this circular cylinder in a flow. In other words, we now know we can generate a thrust from this disc, right? So if I attach the disc rigidly to this, let us say, maybe at some other location, which will drag this body along with that disc, right? Because there is thrust, so it will try to move forward, and so this disc somehow we have attached, this circular cylinder we somehow attached to this disc, right? So it starts moving forward. Now when it is moving forward, we know, so the flow will also, the atmosphere will also move, or the air will also move in the opposite direction with the equal velocity. That means it is equivalent to, say if I have a disc like this, so say this is a V infinity. If the disc is moving with V infinity, I have flow opposite to it at the same velocity, V infinity, right? Assume that it is circular, okay, fine. Now what happens in an ideal flow? So what is an ideal flow? It's a flow of fluids in which the viscous forces are neglected, right? So viscosity is nothing but fluid friction, isn't it? So when an object is trying to move in a fluid, the fluid tries to resist its motion, right? So that's nothing but, viscosity is nothing but fluid friction. So ideal flow, let us consider ideal flow over bodies, right? So if I see, the main aim of looking at the flow around this object is whether this flow can create any pressure difference here, so which can generate lift here, or say which can generate a force that acts against weight of this body, right? That's the whole idea. So for that we are trying to first look at what is an ideal flow, what happens when there is an ideal flow across this cylinder, right? So the ideal flow means what? We have neglected, or say no viscous effects in the fluid flow, right? No viscous effect in the fluid flow, right? So the study that talks about this is known as hydrodynamic theory. Theory talks about this in viscid flows. deals with envisaged fluid flow. So the important prediction, one of the important prediction of this hydrodynamic theory is that, so when there is flow across an object, so the flow has to close behind the object, right, no matter what the shape of the object is. Okay. So we'll look into that. So So this is my one of the stagnation point. So more or less tries to achieve the same profile, right? So more or less tries to achieve the same profile as the profile of the flow, which is ahead of this object, right? So even after the profile behind the object is more or less same as profile ahead of the object. So in this, so this one of the important predictions of the theory is the flow has to close behind the body no matter what the shape of the body or the body shape is. Right? So it also claims that no energy loss throughout the flow. Right? So, but in reality, for real fluid flows, there is definitely some viscosity, right, to some degree, isn't it? And due to viscosity, what happens is the fluid particles try to stick to the surface of the body. In other words, so the velocity of the fluid particles on the body surface is equals to 0. So this is contradicting the ideal flow theory, right, where the ideal flow theory predicts that the fluid velocity on the body will be equal to the flow velocity or even more than that, right. So what is that? So but real fluid flow has viscosity, right, to some degree or of varying degree. And also due to which so in other words, what we can say from here, so the velocity of fluid on the body surface will be 0. Right? So this is in contradiction to ideal flow theory, which predicts that the velocity on the flow on the body surface can be or more than equal to or more than the free stream velocity, right? So but the above theory or the aforementioned theory predicts finite non-zero velocity on the velocity of the fluid on the body surface. Yeah. Okay. In fact, this theory considers the body surface or the boundary of the object as a part of the flow itself. So, if you look at this particular streamline, this is known as stagnation streamline, where so the body itself forms the stagnation. On the body, there are two stagnation points here, S1 and S2, and this itself forms this particular stagnation streamline here, right? So, at these 2 points S1 and S2, the pressure is 0 here. Sorry, the velocity of the fluid particle is 0 at these 2 points S1 and S2, right? Okay. So according to this theory, so we have finite flow, we have finite velocity of the flow on the object, right? So which can be more than the free stream velocity as well, right? So in this particular case, the object, boundary of this object or the surface of the object itself is a part of the flow, which is the which forms the stagnation streamline of this flow, right? Let S1 be the stagnation point, which is on the front part of this body, and let S2 be the second stagnation point, which is on the rear part of this body, right? So now along the stagnation streamline, the flow initially, which is at rest, try to accelerate, right, and reach certain velocity and then drop back to 0 velocity at S2, right? And then yeah. So let's look at what is the pressure distribution because of this flow. That is what we are more interested in, isn't it? So because of the stagnation points, we have positive pressure, right? And as the flow accelerates, the static pressure decreases. Let's call it as negative pressure, because we are not adding any energy in this entire part. So we have a total pressure P naught here, right, which is completely the static pressure at the stagnation point. As the flow accelerates, the stagnation, the dynamic pressure increases and the static pressure drops down. Right? This is the representation of static pressure here. So, right, and the flow, and then again drops back to 0 velocity after reaching certain velocity. It will again drop back to 0 velocity at S2, right? So at S1 and S2, we have stagnation points where it is total static pressure, right? And here on the surface and below the surface, there is certain velocity for the flow according to this theory. So because of which there is a drop in the static pressure, because the total pressure still has to be same here, right? So there is a drop in static pressure. That drop in static pressure, let us call, compared to the ambient conditions, right? So let us call it a negative pressure here. We'll discuss about this negative pressure in detail very soon. Negative pressure, and we have positive pressure. So on both the sides we have positive pressure, and from on the top and bottom we have negative pressure. Similarly, let us look at ideal flow around a streamlined body, right? Okay. So you have the initial stagnation point and the boundary itself forms the stagnation streamline, right? Let S2 be the stagnation point, second stagnation point behind to this flow, right? Okay. So, since according to this theory the flow can't separate from this body, it has to close, it will try to curl around this particular trailing edge and then closes the flow, right? So, you have two stagnation points again here in S1 and S2. If you look at the pressure distribution here, so similar to that we have positive pressure near the stagnation point, right? And then negative pressure on top and bottom sides of this aerofoil. So, this particular streamlined object is known as airfoil, right? So, let us say this is our airfoil and this is negative pressure and this is positive pressure. Okay. So, what we are talking about this is ideal flow or typical ideal flow over bodies, right? So, this is what this figure is talking about. So, we have a bluff body and we have a streamlined body here. So, this is how a typical pressure distribution is. Okay. Let us look at the velocity distribution here. So, V upon V infinity, say V infinity be the local velocity, or say V be the local velocity and V infinity be the free stream velocity here, right? So, let theta represents the location here. So, 0 corresponds to stagnation point 1 and say 180 degrees corresponds to stagnation point 2, right? So, for a circular cylinder, a typical variation is something like this, right? And for an airfoil, so this corresponds to circular cylinder, right? And this corresponds to airfoil. Okay. So, if we can observe for a circular cylinder at maximum thickness point, say P, this corresponds to the maximum thickness point, right? So, with respect to flow, so the maximum thickness point is at 90 degrees, isn't it? Theta 90 degrees. So, this is theta is in degree. So, this is the maximum thickness point for the flow. So, at this flow, it is almost the local velocity is almost twice that of the free stream velocity, if you can observe, according to ideal hydrostatic theory. which is the ideal flow theory we are talking about. So according to it, the free stream velocity at this maximum thickness point is about twice the local velocity is twice the free stream velocity, right? So, but will it happen in reality? But what happens in reality? As we mentioned earlier, so real flows have some viscosity, right? So the flow which is close to the surface of the object will experience a lot of retardation due to viscosity, and then it comes to rest on the body surface. Am I correct or not? So within certain distance, within certain distance from the surface of the body, the flow will try to reach the free stream velocity within very short distance, right, from 0 to the free stream. 0 because it has fluid friction, right? So it will stick to the surface, and on the surface the velocity is 0 for the fluid flow, and then it will reach the free stream velocity within small distance from the surface. Let's say if you take a perpendicular distance to the surface, so within a small perpendicular distance from the surface, it will try to reach to the free stream velocity at that particular location. So this small thickness in which the velocity reaches from 0 to the free stream velocity, close to the free stream velocity, is called boundary layer, right? Okay. So we'll see why we are talking about boundary layer at the same time, right? So because we are dealing with not ideal fluids, right? So we are talking about air flow of air around the body, around the streamlined body, to be frank. So we need to know how this air, which is a real fluid, behaves on this particular object, right, at different conditions. So that is what we are trying to do. So from there, how to get the lift, right? How lift is generated, which is our main aim, right? We know how thrust is generated right now, and now we would like to know how lift is generated. By the way, when we are talking about the thrust generation, we are talking about reaction from the air, isn't it? So the disk is rotating, and which in our case it's a propeller, say. So the propeller is rotating, which is pushing air behind, and then air is pushing this propeller forward, isn't it? So this is producing, this particular phenomena is producing certain thrust, right? So similarly, if there is that is in fact creating a pressure difference across the disk, right? That is what we witnessed. And why we have to depend upon air to generate thrust? Because that's the only medium on which we can apply force, right? We can get reaction from. For example, if you're talking about car, your car wheels are connected to the engine by means of some drives, right? Gearbox, and then there is shaft, axle, and then there is shaft, right? So you have certain linkage that is the tires of your car is connected with your engine, right? So what happens is, when there is power to this engine, when the engine starts generating the power, it will start rotating the shaft, right, and which in turn rotates the wheels, right? So the wheels, because of the friction on the ground, gets a reaction force, right? Am I correct or not? So on the ground it is opposite direction, it is backward, but on the tire the friction acts in the forward direction, which is taking you forward, right? So friction helps your car to move forward. If you put an ice in beneath it, your tire will start slipping, you will not be able to move forward, right? So the car is moving forward because with the help of friction. That means you are getting reaction from the friction, due to friction, reaction from the ground due to friction, right? So your car is still in atmosphere, but you are using reaction from the ground, isn't it? Right? But when you are off the ground, the only medium which can give you the reaction force is air, right? So that means that's the reason why we are depending on air for generation of thrust, right? Similarly, we have to depend on air, of course we know that, for generation of lift, isn't it? So if you want to know how this air behaves in reality on this, then we need to talk a bit about this boundary layer theory as well, right? So that will help us to understand why there is a flow separation, or when we talk about the aerofoil, so this streamlined body is known as aerofoil. So when we talk about the characteristics of aerofoil, we'll be using this flow separation concept, right? So in order to understand what is flow separation, how it happens, we first need to talk about boundary layer. So this lecture may be with bit more aerodynamics, right? So maybe boring to some of you, but still there is no shortcut. We have to go through this lecture, right? So let us say y be the perpendicular distance to the surface, right? And then say v infinity is a corresponding velocity let us say v1 be the local velocity here, okay. So on the body, when y is 0, which is on the body, the velocity of the fluid is 0, and it slowly increases to the free stream velocity. This is almost close to that point, we can say, no? Let us say. Okay. So this is almost close to that point. So this is, right, this is the loss. Okay, we'll talk about this, but first let us look at this curve, right. So the velocity gradually, see, this talks about the magnitude of velocity. Let us say if I have an object like this, right. So at this particular say point, say this is my tangent to the surface and this is my normal to the surface, right. So along this normal, let's say there is flow here, right. So this object is in flow, we place this object in flow. So at this particular point, what is the corresponding magnitude of velocity? It's not that these arrows doesn't mean that the velocity at this particular point, you know? These arrows represent the magnitude of velocity at this particular, at these different points, that's it, right. So arrows represents the magnitude at this particular point. If you have, so multiple those pitot tubes, let us say, or say static tubes, multiple of the static tubes arranged in a stack, right. So if you have a vertical column and you have perpendicular to it, we have multiple ports, and then use that particular frame with multiple ports to measure this particular velocity profile, right. So a thin layer in which the velocity of the flow rise rapidly from 0 to free stream or local velocity. Say V1 is known as boundary layer. Right. Okay. So Prandtl in the year 1904 proposed this theory, right. So he postulated that this delta, right, is a thickness of the boundary layer is far less compared to, or very small compared to the dimension, characteristic dimension of the object. Let us say in this particular circular cylinder case, we can consider the characteristic dimension as the diameter, right. So in this particular case, we can consider some length which can join, right, the first point and the last point here, right. So that can be the characteristic length here. So according to this, according to him, this delta upon L is far less than 1, where L is the characteristic length. Fine. Now typically, so within this delta, so all the inviscid or viscous effects are dominant, right. So we can say, So these viscous effects are confined within this particular boundary layer, right? And also outside this boundary layer, we can deal with the same potential flow theory or the hydrodynamic theory. We can use the same principle. So outside this boundary layer, the fluid flow behaves as if it is inviscid. Right? We can consider the conditions to be inviscid. Right? Yeah. So now what happens actually? So when you have an aerofoil, say this is your given object, right? So say, let's say this is your given body, right? And then there is flow. You have a boundary layer, right? Okay. So you have given body with boundary layer, right? So what's happening within boundary layer? We know the velocity at any given point will raise from, at any given point on this airfoil, will try to raise from 0 to the free stream or the local velocity at that particular. So it is same as here, same for here. So it depends, no, how the pressure is, right? So the velocity keep changing from 0 to free stream velocity, right? And more, when you say 0 velocity, what do you mean by that? Are you not bringing the particle of mass m to rest at that particular point? Isn't it? So is it nothing but you are accumulating mass, isn't it? Am I correct or not? So a concept of equivalent body is introduced in order to, so what happens is, so we can actually replace this particular boundary layer with this body by means of a body of thickness delta star added to this particular given body, right? So we have the boundary of this given body and add a delta star thickness which accounts for this boundary layer effects, right? So add that particular thickness and replace this body with that particular thickness, then what you have is a potential flow solution or ideal flow solution, right? So all that viscous effects are now constrained within this delta star, and then delta star is now become a part of this body itself, right? So that is what we call it as equivalent body here, right? So how it is? Okay. So according to Kutta condition, right, the flow has to leave parallel to this trailing edge, right? So you can read about that. So this, so we can replace our given body by means of this equivalent body, right? And consider the flow is inviscid. And you can figure out what is the corresponding pressure distribution as well as velocity distribution using ideal flow theory. So what is this called as equivalent body, right? Fine. So according to this equivalent theory, right, so what we are doing, we are displacing this boundary layer or the surface of the boundary by means of an equivalent boundary layer thickness, right? So let's say delta star represents the equivalent boundary layer thickness. Say this is my delta star. So let's say delta star represents equivalent boundary layer thickness. So why we are using this equivalent boundary layer thickness? So if we shift the flow by this particular delta star, right? In delta star, what is happening? So we are losing some mass flow, isn't it? Whatever the mass that is entering, if you consider a particular control volume, whatever the mass that is entering may not be leaving because it is being trapped in this particular boundary layer because of the retardation that the fluid element faces, right? Isn't it? So the bottommost particle will faces the retardation, more retardation, isn't it? Higher retardation compared to the others here. So that's why it will come to rest soon compared to the other particles or particles in the above layers in that particular boundary layer. So what we can say is, say at a particular location, say this is my y, right? Say consider a small element dy here, right? So where vy is the corresponding velocity at that particular location. Got it? And then what is this difference? So this particular difference will be v1 minus v of y. V of y is the velocity at that particular location. So mass flow rate, or v1 minus vy represents this particular loss in mass flow rate, mass flow, isn't it? So this mass flow is equals to the loss in mass flow. This talks about the loss in mass flow. So the total actual mass flow should be what? Rho a v1 ideally it should be, but because of this, so in this particular strip what you have is rho a vy, where a is the cross section here. Let us say if you have unit depth, unit depth into this, what you have is the area of cross section of this thin strip will be, let us say if you extrude this strip outside, right, you have this dy, let us say this depth be unit, right. So dy times 1 will be the corresponding cross section through which it is the mass flow is happening. So that is rho a dy, a is nothing but rho times dy times 1 times vy will be the corresponding mass flow through that particular strip in the boundary layer, right. And then what will be the loss of the mass flow? It is like rho a v. Ideally when there is no, for an inviscid flow, the velocity on the surface will also be equal to the velocity v1 here, right, isn't it? So in that case the total mass flow should be rho v1, right, minus now you have, yeah. So across this strip it should be rho dy times 1 times v1, right. So the same strip is now, in the same strip because of this boundary layer we have what, rho a is nothing but dy times 1 times vy, v at that particular location, isn't it? So subtracting these two, what you have is the mass flow that is lost, this particular thing. So the mass flow that is lost is rho, corresponding cross section area is dy times unit depth times what is the velocity? This is the loss in velocity. Am I correct or not? So this, if you integrate it from 0 to infinity, right? So at a location when vy becomes v or 0.99 times of v1, right? So this particular integral will not have any meaning. So you can say 0 to some value where dy value, where this velocity becomes velocity, local velocity become velocity at that particular y location becomes local velocity, close to local velocity, right? So this must be equal to, so again coming back to this equivalent body. So what is the concept here? So we are replacing, so in a inviscid flow, let us say, now we want to find a way how to get this solution, right? Am I correct or not? How to figure out, so coming back to this equivalent body, what we have is delta star just to replace the given body, right, so that the flow solution becomes inviscid flow solution, right, isn't it? Okay. So that means, so whatever the mass flow rate that was lost must be compensated by this delta star. Am I correct or not? So let us say the mass flow rate compensated by this is, delta is the thickness, right? Thickness and unit depth will give you the corresponding cross section area times the density here times the corresponding velocity will be V1, because for an inviscid solution even the velocity in the boundary layer will be same. If you use the equivalent boundary layer concept, the velocity in that boundary layer should also be same. Let us say, yeah. So here this must be the delta star. Okay. So this is your delta star, that y, and then unit depth. If you extrude it out, unit depth. So delta star times 1 is the area, corresponding area, density times area times the corresponding velocity. The concept is it should have, for an inviscid flow, it will be equivalent, right? It will be equal to V1. So what we have is delta star is equals to 1 upon V1 times 0 to infinity rho times. So let us say if you consider incompressible flow. So I am taking density out, what I can have is V1 minus V of y the given location times dy, assuming flow is incompressible. Okay. So this is what we are going to have. So you can further take it in saying 1 minus V of y upon local velocity times dy. Right. So you can look at the detailed derivation. This is just like it's a one-dimensional thing that we have used. You can look at the detailed derivation for this. Okay. Let's talk about flow separation. Since we know what is boundary layer and equivalent boundary layer, concepts of boundary layer and equivalent boundary layer, we now try to use them for our concept of flow separation, right? Okay, so according to ideal flow theory, what it predicts? So according to this, we have one stagnation, S1 and S2 are stagnation points, right? Which is on the front and on the rear sides, right? Rear side of the object, isn't it? So according to this, so there is, and then the flow reaches some maximum velocity on the surface, right? Maximum velocity on surface downstream S1, right? And drops back 0 at S2. Am I correct or not? So due to which there is pressure in the front and pressure in the back, positive pressure acting in the front and back, right? So the force generated, or the net force generated by this, by the pressure acting on the front and the rear side of this object, of this cylinder, will be cancelled out, isn't it? So there is, so similarly there is a stagnation point in the rear end of this object. So this force in the front end and the rear end will get cancelled. Force because of this pressure acting, right, at these stagnation points will cancel out. That means it will result in 0 net axial force, right, or net axial horizontal force. There is no net horizontal force, 0. I'm trying not to use these words drag and lift for the time being. We'll soon define them, and then we can start using them, right? So till then, let me talk in terms of axial force and then vertical force here, okay? So 0 axial or horizontal, I should say, horizontal force here, right? And then 0. Similarly, you have negative pressure on the top and negative pressure on the bottom, right? So because of which this negative force because of this negative pressure cancels out, and there is no force or net, or 0, no net vertical force. Right. So let us look at an analogy in order to understand what happens in reality for this flow, right? So this is again from the ideal flow, which we just discussed. We'll talk about this in detail, or say we'll talk about the actual flow once we look at this analogy. So let us consider a road which is flat on the top, and then there is a slope down, and you need to climb the slope up, and then there is a flat road which is almost at the same height, right, of this initial road, which is here. Okay. Let's say if I'm on this skating board, right? Let's say I'm on this skating board. So let's say this is point A, which is at a height h, right? So it possesses some potential energy definitely. And now as you go down this slope, right? So my potential energy is converted to maximum kinetic energy at point B, right? And then ideally, I should reach point C attaining same potential energy which is at point A, right? This is when there are no losses. But when there is loss, see, of course there is friction here, friction generates heat, and there is loss in energy. So you may not be able to reach point C what you desired, but practically you may end up reaching point C prime here. Right? Isn't it? So the desired point is C, you may end up reaching C prime because of the loss in energy. So similar thing happens in real flows as well, right? So let us look at that. So say this is my S1 and this is my S2. That is what we have, right? Isn't it? For this circular cylinder. Now say, so at S1 you have high static pressure, isn't it? High pressure. And according to ideal fluid flow, where there is no viscosity, you achieved a maximum velocity here, right? Which is, so that means when you have maximum velocity, what you have is low pressure, low static pressure here. Am I correct or not? And then there is some, again, high static pressure. And there is no loss of energy in this entire process for this ideal flows, right? So what happens, we know how gas flows, how a fluid flow. When do a fluid flow? So from high pressure to low pressure, when there is a pressure difference, from high pressure to low pressure, the fluid flow happens, isn't it? So such a condition is a favorable condition for us, isn't it? So what we have is, pressure gradient. Gradient is change, right? It's a slope. Yeah. We have a favorable pressure gradient, right, when reaching from S1 to this particular point P. Fine, isn't it? So in inviscid flow, what happens? Say this is my local velocity. So what I have is same local velocity perpendicular to the surface starting from the body. Am I correct or not? Say this is my local velocity V1 at this particular location, isn't it? And here I am reaching almost twice that of the free stream velocity, 2 times V infinity here. So, right. So, and then what's happening? So we have high pressure here and we have low pressure, because of which the fluid retards, isn't it? It's an adverse condition. Flow. So you are trying to, here the fluid here is trying to push itself from low pressure to high pressure, right? Which is an adverse pressure condition for us, which is known as adverse. So this particular direction is adverse pressure gradient. Am I correct or not? So again, from the ideal fluid flow, so close to this it is 0, and then ahead of this the velocity reduces compared to that velocity at point P, and this velocity will be equal to the local velocity at that particular location. Am I correct here? So, but for real fluids, real flow, what happens is, right, this is how the velocity profile will be. Am I correct or not? Right. So the fluid elements, so let us say this is my point A here, right. So let us look at what is A prime, right. What happens at A prime? So if I draw a perpendicular to the surface here at A prime, right. So the fluid element which is having certain velocity here, because of the adverse pressure conditions and also because of the fluid friction, it will try to retard, isn't it? It will, the velocity profile will completely changed compared to that of what is A. So the fluid may be something like this, right? So say that V1 is the local velocity at that particular location. Am I correct or not? So let us move ahead and then go to this point A double prime, which is here, and see what happens now. Now say the innermost particle which is on the surface, because of this adverse pressure, it is opposing, right? This pressure is opposing it, opposing the flow. So it will retard these molecules to rest. Is it? Am I correct or not? So that means the pressure profile here will be completely different, where the molecules in this boundary layer may almost reach the, so the molecules on the surface definitely is at 0, velocity is 0, and in the boundary layer as well, it has come to rest, almost to the rest. Now if you move ahead, what happens here is, there can be a reverse flow happening, right? Because, so the molecules now, these molecules are at rest, these fluid molecules here, fluid or the fluid elements. So there will be a reverse flow from high pressure to the low pressure regime here, and then there is something called flow separation. So the flow tries to separate from this surface. This is called flow separation, right? And what you end up seeing is a vortex formation here. What you have is vortex formation, right? So this, under the adverse pressure conditions, there will be a flow separation from the surface. So when there is flow separation, the pressure distribution on the body will altogether get redistributed, right? It will change. The pressure distribution completely changes compared to the attached flow condition, right? So we'll use this flow separation concept very regularly in the coming lectures, right, to at least while discussing the characteristics of aerofoil, right. So, thank you.